The 2010s was an interesting decade for software development. Some of the highlights include the gold rush of mobile apps, the move towards cloud services such as AWS, and a number of programming languages that many of us would end up falling in love with. Baked into these new languages was a greater emphasis on runtime safety, and for good reason. Runtime errors are pretty much the bane of software developers, with a large amount of time being spent to both prevent and mitigate them. In languages such as C and C++, the most common runtime error is the SIG-SEG-V, which stands for a segmentation violation or segmentation fault. This error occurs whenever a program attempts to access memory it's not permitted to, such as indexing an array beyond its bounds, writing to a memory address that belongs to another process, or the most common cause, attempting to dereference a null pointer. In fact, this last cause is so common that a number of solutions have been created to solve this problem. These solutions are known as null safety, and I'd argue they're one of the greatest features of modern programming languages. The most common implementation of null safety has involved the use of a special type, inspired from functional programming languages such as Haskell. Now, Haskell is a bit of an edgelord, and calls this type the maybe type. However, in other languages, it's simply referred to as an optional. The implementation of this type is actually rather simple, and is basically a union or enum to represent either one of two values. The first of these values is sum, also called something, and represents the existence of an underlying value, which is also contained within the type. The second of these values is none, or nothing, and represents the absence of a value, similar to null. The benefit of using an optional is that it pushes the handling of the none or null value into the type system. By doing so, it moves the error handling out of the runtime into a compile time check. This requires developers to explicitly handle the null case before their code can even be compiled and deployed. Moving errors from the runtime into compile time is a very good thing, and because of this, optionals can be found in a number of different languages. Newer languages, such as Rust, Kotlin, and Swift, provide the option, nullable, and optional type respectively. Even traditional languages, such as Java and C++, support optionals as well, with Java adding the optional type in 2014, and the king of runtime errors provides std optional since C++ 17. Notably absent from this list, however, is Go, which does not provide any real null safety, something I personally have a problem with. However, that's a video for another time. To gain an understanding of how the optional works under the hood, I've created a rather simple implementation in Rust, which is just an enum with a generic type. This enum provides the two values we mentioned earlier, sum and none. The main thing to note is that our sum value has associated data, which matches our generic type. In order to use this type without any methods, the compiler requires us to use pattern matching in order to handle either of the states that the optional can be in, whether it has a value or not. This implementation, whilst naive, is actually very similar to how Rust implements option under the hood, albeit with a few more macros and methods. Despite being simple, this implementation shows us that there are two features a language needs in order to support the optional type. The first feature is generics, which allows the optional to wrap the associated value, keeping it type safe. Although not strictly necessary, I haven't found an implementation that doesn't use them. The second requirement is for the language to be compiled, otherwise that defeats the purpose of a compile time check. So given these requirements, how then do interpreted languages such as JavaScript provide null safety? Well, they do so using a feature called safe navigation. Safe navigation, also known as optional chaining, first appeared in the Groovy language back in 2011, and provides a means to safely interact with a potentially null value at runtime. To do this in JavaScript, you simply use the question mark operator before calling an object's method or property. If the object is null or undefined, then the operator will short circuit and return an undefined value rather than throwing an error. Given this behavior, it makes it possible to chain this operator as you call nested properties of an object. And whilst it's not as effective as compile time safety, it certainly reduces the boilerplate of having to write if statements with a lot of Boolean ands. Additionally, the use of linters can also help to reduce the risk of errors. One such option is the no unsafe optional chaining rule in ESLint, which can be used to reduce any type errors when using safe navigation. As well as JavaScript, this feature is also found in Ruby, which instead uses the ampersand symbol, given that the question mark is already used by methods to mark a Boolean return value. Whilst both JavaScript and Ruby support safe navigation, one language that does not is Python. And despite a proposal being raised in 2015, doesn't look like it will anytime soon. As well as interpreted languages, safe navigation has also made its way to compiled ones. Swift added the feature the same time that it did optionals, requiring the use of the operator in order to unwrap an optional safely. Rust also provides safe navigation as well. When inside of a function that returns an option, any internal options can be unwrapped using the safe navigation operator, which, if the option is none, will short-circuit the function and return none early. This behavior again is inspired by functional programming languages. In fact, the maybe type in Haskell that we mentioned earlier is actually a monad, which provides this chaining feature. Ultimately, the inclusion of null safety in many modern and traditional languages is something I'm happy to see. Newer languages such as Rust, Swift, and Kotlin put a lot of emphasis on runtime safety, and by doing so, means we get to spend less time fixing bugs, and more time writing code that we can feel just that little bit more confident about.